In today's talk, we're going to continue to develop some of the fundamentals that we're going to need to get our main result that will allow us to count the number of orbits, which then will tell us the number, for example, in the problem we've been working on, the number of different ways you can sit, in this case 6 people of 2 types A and B around a table, or in general, the number of ways we'll be able to count all sorts of different patterns subject to certain symmetries. So remember, if we're looking at seating 6 people of types A and B around a table, we can model that by looking at strings, 6-letter strings from the set AB. I'm going to model these strings here by putting the letters A and B around the table. And if I think of starting here, this first string AAA, AAB would correspond to this seating arrangement around the table. I've listed all 64 strings here, just as we did at the end of the last talk. And just like before, I've arranged them by their orbits. Each line is a particular orbit. You can see that the second string is just a rotation, R1 of the first string. It would be starting here. So if I change my starting location to here, A, B, A, that would be this string. This would be the same thing rotated one more unit, one more, and then we get back to the beginning. So I've listed all 64 strings arranged by their orbits. And the goal, remember, will be to count the orbits, because each orbit represents different strings that all count as the exact same table seating, because they're all equivalent to each other by rotations. For many, the orbits have length 6. For some, like AAB, the orbit has length 3. For some, the orbit has length 2. In fact, just this one, AB, and BA. And we have some that have orbits of length 1. If you have all A's around the table, there's no other string in the orbit. So in total, one can just see, just counting directly, there are 14 different orbits. Our question is, how can we approach a computation of this number that we'll be able to generalize? And here's one trick which I'm just going to state now, and we'll come back to it much later. We want to count the number of orbits, so somehow we want to count 1 for each full orbit. Well, one way to count exactly 1 for each orbit is to assign a numerical value to each string. And if I assign exactly the reciprocal of the orbit length, here we have an orbit of length 6. So if I assign 1/6 to each and every string that has an orbit of length 6, then the total orbit, when we add it together, gives me 1. And I do the same for all of these strings, all of these strings, all of these strings. Basically, for all of these strings and all of these strings, I assign 1/6, or the reciprocal of the orbit length. For all of the strings in here, I assign 1/3, etc., 1/3, so that the total sum of these values that I've assigned to the strings is just 1 for this entire orbit. And I do the same for the strings in this orbit. For these, I assign the value 1/2, and for these, I assign the value 1, because their orbit length is just 1. So somehow, if I were able to do this in any sort of efficient way, I could get the total number of orbits just by adding these values that I've assigned to each and every string. Of course, that doesn't really help me any at this point, because it's hard to know ahead of time without doing this computation for each and every string what number to assign it. And if I do that computation, I might as well just list all the orbits and count them directly, which is what we already did. But we'll see that this gives us some insight into what will in the future be some much more efficient ways to compute the number of orbits. In order to get started with that, I want to talk about the rotation group. We've already seen that these are the different rotations that are available when we have a 6-letter string that we put around our table. So here's our example. A, A, B, the 6-letter string. And we've already seen that R naught, this is just what we'll call the identity. We apply R naught to a string, to any string, and it leaves it alone. R naught on A, B is just A, B. Leaves it alone. It leaves every string alone. It's the identity element in our group. And I'm using the word group. I know most of you haven't studied group theory, and you're not going to need any fancy theorems from group theory, but it's going to be important that these rotations form a group. A group is just a set of objects, in this case the rotations, that have an identity element and some notion of a product. And let me show you what I mean by a product. R1 is our rotation by 1 unit. Our product we'll just write like a product, R1 times R1 like that, and that will just mean do R1 and then do R1 again. So product will just mean composition here, do one and then do the other. And it's easy to see that if you do R1 then do R again, you get R2. Moving 1 unit and then moving 1 unit again is just like moving 2 units to begin with. R1, R3 is R4. R1, R5 is just R6. There is no R6, but R6 you can think of as going around being exactly the same as R naught. Back to the identity. And you can write R2, R4 is again the identity. So to be a group, you need this operation, which in group language you'll often call multiplication. Here it's just this composition, do one, then do the other. You need an identity, which is R naught, and the identity has the property that R naught, R1 is the same as R1. R naught, R2 is the same as R2. In other words, multiplying any element by the identity doesn't change it, and it's clear R naught satisfies that. And you need inverses. I won't write down the details, but basically if you do a rotation by 2 units, you need a way to get back to the identity. Well, if you rotate by 2 units and then you rotate by 4 units, you're back to the identity. So the inverse of a rotation by 2 units is just a rotation by 4 units. The inverse of a rotation by 3 units is again a rotation by 3 units. So R3 is the identity, R naught. The inverse of R5 is clearly R1, and the inverse of R1 is clearly R5. So every element has an inverse. The identity, of course, is also its own inverse. And these rotations as a whole form a group. And again, don't worry about these group properties, but they'll just allow us to manipulate the rotations very easily. Let's ask about formally what happens if we apply each of the rotations to a particular string. And I say formally, we're going to talk about a sum here just by not adding numbers or anything, just doing a formal sum of these symbols. What happens when you take R naught times this string, R1 times this string, R2 times this string, etc.? Well, let's answer that question. What do we get? R naught times that string is A, B. When we apply R1 to the string, we'll get A, B, A. We'll apply R2 to the string, R3, R4, R5 to the string. R5 is just rotating by 5 units. We get the B, A. And we get the entire orbit. So you'll notice that if you apply all of the rotations to any string, in this particular case, you get the entire orbit. I'm going to skip this. I apologize. We'll come back to things like that later. Let's look at the same. This is what I was just writing down now. Let's apply all of the rotations to a different string, the BBA. Again, R naught times the string is just the original thing. R naught is the identity. R1 gives you that. R2, R3 times the string is this. R4 and R5. And again, you get the entire orbit. But now notice something a little bit different happens when we apply all of these rotations to the string BA, BA, BA. When we apply R naught to BA, 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 of course we get BA, BA, BA. That's just this string. When we apply R1 to that, we get this string. When we apply R2 to the original string, you get back to this one again. When we apply R3, you get this one. When we apply R4, we get the original one. When we apply R5, we get this one. In other words, we've applied all 6 of the rotations to this string, and we've gotten 3 of these and 3 of these. So we'll write that formal sum as 3 times this string AB, 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 plus 3 times this string BA, BA, BA. In other words, we get 3 times the entire orbit. And things are very different if we apply all of the rotations to this string AAA, AAA. Why? Because all of them, any one of these rotations, when you apply it to the string AAA, AAA, you get back the string AAA, AAA. And we're doing that 6 times, so of course we get 6 times this one string, and that one string is its own entire orbit.